Okay, in this lecture, we begin to look at Newton's second law applied to situations involving a rotation about a fixed axis. That is, we take a look at rotational dynamics about a fixed axis. Okay, now recall that a fixed axis is an axis that is at rest with respect to an inertial reference frame. And also recall the following. F equals ma, Newton's second law in its rotational form is as follows. Net torque equals rotational inertia I multiplied by angular acceleration alpha. So we're going to apply this situation to a demonstration that we've seen before, and this is the Atwood's machine pulley setup. So let me go ahead and show you briefly that demonstration once again. I need to retilt my phone. Okay, so bear with me here as I do. Okay, there's my pulley. Okay, so back in our unit on dynamics, we considered the pulley's surface to be frictionless, and when we did, the pulley itself didn't rotate and the string just slipped on the pulley like so. Now we will take into account the pulley's rotation, however. For example, if I release the setup like so from rest, and it rotates in this manner, we of course have already looked at the kinematics of this situation earlier in the unit, but now specifically we're going to see how when we apply F equals ma for a scenario such as this then results in the acceleration that we see. So let's go ahead and turn this example into a problem. I'm going to retilt my phone here, so bear with me as I do. There we go. Okay, and now copy the problem down into your notes. As I read it to you here, I will have to reposition my file. Okay, a string is draped over a fixed pulley that rotates on a frictionless axis. So the axis of rotation itself is frictionless. Okay, the string has two masses attached, 1 and 2 kilograms respectively at opposite ends. I'm just making the scenario here easy to deal with in terms of the numbers. Okay, the string does not slip on the pulley. Okay, the pulley is a disc with a mass of 1 kilogram and a radius of 10 centimeters. Once again, I'm just making up easy numbers to work with. Let's then go ahead and find the acceleration. Okay, so let's go ahead and draw this out first. Like so. So here's our pulley like so, and then right here is the fixed axis. The axis itself is perpendicular to the board like so. Okay, I'm going to say that the pulley has a mass M3 associated with it. That's given to us as 1 kilogram. And it has a radius, capital R, that's given to us as 10 centimeters, so that's 0.1 meter. Okay, and then I have my masses attached to the string. So right here off to the left is the lesser mass, M1 equals 1 kilogram. Right here to the right, like so, is the greater mass, M2 equals 2 kilograms. And then as you saw, the scenario gave us an acceleration that looked like this. Okay, now let's go ahead and just approach this problem first of all as if we would have done back in chapter 4 by taking a look at F equals ma, the forces that are exerted upon the masses. So let's take a look at M1 first. Okay, back in chapter 4 we would have said the following. Okay, for M1 we have the tension vector like so, and then the weight M1g like this, and the acceleration is in this manner. So we would then add up the forces. T minus M1g is equal to M1a. And there's the first of our 2 equations and 2 unknowns. And now let's take a look at M2. Okay, so for M2 we have tension like so, and then M2g. Here's the acceleration A. Add the forces. M2g minus T is equal to M2a. 2 equations, 2 unknowns, blah, 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 as we saw back in chapter 4. However, now let's take a look and see what happens with the torques applied to the disc if the tensions are the same. I'll do this on the lower board. So now let's take a look at the disc. Right here is M3, radius capital R. Right here is the axis. Okay, now tangential to the disc, we have the tension forces being applied to the disc. So for example, right over here, off to the left-hand side, is the tension like so that is being applied due to the string on the left. Right over here, however, is the moment arm, capital R. So off to the side, here's capital R, and here's the tension T like so, and they're at right angles with respect to each other. Let's now go ahead and calculate the torque. When we do, it's R cross F. So R times T in this direction, this then gives us a torque vector out of the board, and it's equal to R times T. Okay, now let's take a look and see what happens here off to the right-hand side. Off to the right-hand side, we have our tension vector like so, tangential once again to the disk. Right here is the moment arm, capital R. So off to the side, here's capital R, and here's the tension T. Once again, they're at right angles with respect to each other. Now calculate the torque here. Do R cross F using right-hand rule. When you do, you get R cross F into the board like so. And it's the same value, R times T. So over here with this diagram off to the left, you do R cross F and you get an RT out of the board. Over here you do an R cross F and you get an RT into the board. Therefore they cancel each other out. Therefore in that scenario, does the pulley itself undergo an angular acceleration? In other words, does it rotate if it's starting from rest? No, it does not. So then therefore in our scenario where yes, the pulley does rotate, what does that then mean about the tensions? They have to be different from one another. So let's go into our force diagrams now, and this diagram here, and name the tensions different values. So over here, let's now refer to this as T1. So then therefore, if we went through F equals MA once again and add up the forces, we would have T1 minus M1G is equal to M1A. Okay, then over here, this value of tension now must be different than T1. Let's refer to this as T2. So then when we add up our forces, we end up with the following equation. So far, if you look carefully, we have here 1, 2 equations, and 3 unknowns. Those 3 unknowns are T1 and T2, and the acceleration A. So then therefore, I need another equation. This obviously comes from setting up a net torque calculation on the lower board. So let's now go back to these diagrams right here. First of all, this tension right here, this is the tension T1, and this tension right here, this is the tension T2. So now here's a T1, and here's a T2. Okay, now because the string does not slip on the pulley, this then means that the tangential acceleration of a point on the rim of the pulley is exactly the same as the acceleration of the objects themselves. This will then allow us, or help us, determine which will be the positive torque and which will be the negative torque. So let's take a look at the two torques. First of all, we have right here an R cross F. I'm going to call this torque here tau 1. So now I go R cross T1 like so, gives me a torque that's out of the board. But look at the direction that my right hand fingers are curling. They're curling in this direction like so, which is opposite of what the direction of the tangential acceleration would be. Say up here at the top of the pulley, the direction of the tangential acceleration would be in this direction to the right-hand side. But when I do R cross F here, notice my fingers are curling in the opposite direction of the acceleration. Therefore, we have to think of this torque as a negative number for that reason. Okay, now the torque vector itself, tau 1, comes out of the board like so. Its magnitude is R times T1, but this has to be thought of as the negative direction. Similarly, over here for this torque on the right-hand side. Now, once again, do R cross F. When you do, you go R cross F like so, and that goes into the board. But take a look at the fingers in my right hand. They're curling in the direction of the tangential acceleration. Therefore, we have to think of that as a positive torque. So this torque vector is into the board like so. We'll call this tau 2. R cross F is into the board, but that's the positive direction in this problem. So tau 2 is equal to positive R times T2. And now we add up these two torques here to get the net torque, and then set that equal to I times alpha. Okay, so net torque equals I times alpha. Here's then how we set up the expression. So we first of all have positive RT2 minus RT1 equals then I times alpha. The I is 1/2 M3 R squared That's the rotational inertia of the disk, and then multiplied by alpha. Recall that the angular acceleration alpha is related to the tangential acceleration through the following expression. A tangential equals r times alpha. So the alpha is equal to A tangential divided by r, but as I've said, the A tangential is the same as the acceleration A of the objects because the string does not slip on the pulley. So then therefore we replace the alpha here with A over r. Notice that in this expression, all of the r's cancel out. So if all of the r's cancel out, then I end up with this expression here as my third of 3 equations and 3 unknowns. Like so. So do the math here and notice that all of the r's cancel out. So now I've got this expression and then the 2 above. This expression here and this expression here. And at this point it just becomes 3 equations and 3 unknowns. And now we just solve for the acceleration A. So let's go ahead and finish the problem. Okay, and then the easiest way to do the algebra very simply is to, first of all, take this expression here and solve it for T1. That equals this. Okay, take this expression here and solve it for T2. Okay, just be careful when you move some negative signs around. When you do, T2 is this. And now we take the expressions and plug them into here. Okay, so T2 minus T1. So here's T2, what I just wrote down a moment ago. Okay, minus T1, so minus this, equals then 1/2 M3A. And now we just solve for A. So take these 2 terms and move them to the other side. Do a little bit of factoring as we do. Like so, and then divide by the parentheses. We go like this. There we go. Like so. Okay, and then at this point, let's just go ahead and calculate our number to complete it. Okay, so let's see, number-wise. We have here 2 times 9.8 minus 1 times 9.8. Then all divided by 1 plus 2, which is a total of 3, plus, oops, there's no A here, sorry. I have 1 plus 2, which is 3 plus 1/2 times 1. So this is a total of 3.5. So divide by 3.5, and this then gives us an acceleration of 2.8 meters per second squared. Okay, now if we did not take into account the rotation of the pulley, in other words, if we went back to our problem early on in our unit on dynamics when we looked at the Atwood's machine, go back in your notes and check this if you have to, the acceleration would have just been this quantity right here. Notice that the acceleration, when we do take the rotation of the pulley into account, is less than it would be if we did not. The reason for that is because some of the potential energy of the falling objects is being converted into, yes, the kinetic energy of the falling objects, but also rotational kinetic energy of the pulley itself. We'll treat rotational energy at a later date.